Hello everyone, today we're doing chapter 11, problem 28, and this problem asks us to determine the IUPAC naming for each of these alkynes. So we can start with remembering how the rules for naming molecules. So you always want to find, or at least I like to find always, the parent chain first, and then determine any substituents that are bound to it. So we're given some sort of chemical formula here, but these are kind of hard to read and understand, so I always like drawing them out myself. So we can see that we have 1, 2, 3. So 1, 2, 3. And then we have a CH3 bond. So we know that that's going to just be sticking out. CH3. And then we have a carbon. And then triple bond. And then a carbon, which is here. And then 2 more carbons. So this is the structure we have. And let's do the same for all of these, actually. So for this one, we have 2 CH3s. 2 CH3. The central carbon is right here. Then we have another carbon, which is your alkyne is attached to. And the second carbon of the alkyne, 1 more carbon here. Then again, 2 terminal carbons coming out. And then for C, we now have 2 ethyl groups. So I can draw that. So we have 2 ethyl groups with the central carbon here. And then we have 1 more carbon before we have the alkyne, then the carbon of the alkyne. We have 1 carbon here. Then we have 1 ethyl group. Then we have another carbon on the parent chain, and then we have a methyl group. Then we have 2 more carbons. And for this one, we obviously have our alkyne first, carbon, carbon, then we attach 1 more carbon, then we have an ethyl group, and then we have 1, 2, 3 carbons after that. 1, 2, 3 carbons after that. So here we have 1, 2, 3 carbons, 1, 2, 3. Then we have our alkyne. This is the carbon of the alkyne. Then we have 1 carbon here, 1 more. You have your alkyne carbon. Then you have your final methyl right there. So now we've drawn every possible structure for this for all the problems here. So now let's identify the parent chain. So remember, your parent chain must include your alkyne, and not only that, your alkyne must be positioned at the lowest possible number. And then we can add all the functional groups after that. So parent chain with alkyne lowest possible number, parent chain being the longest straight chain carbons. We have 1, 2, 3, 4, 5, 6, 7. Obviously, this gives us alkyne at 3 position. If I were to count from the left side, I would have 1, 2, 3, 4, 5, 6, 7. So we know that we should count from the right. So alkyne will be given position or position number 3. Whoops. So if I actually just move that down, we can see that for A, because we have 7 carbons, so that's going to be hept. And we know that we have the suffix is -ine, not heptane. It's -ine for the alkyne. And where is that alkyne? Well, it's at position 3. And now, what are the functional groups attached to it? Well, we have a methyl group attached to it. So we have a methyl at 1, 2, 3, 4, 5. We have a methyl at carbon number 5. That's the name of this structure. Next, for B, once again, identifying this longest straight chain, 1, 2, 3, 4, 5, 6. But you can see this molecule is symmetrical, so it doesn't matter which side we write on, or which side we start counting from. So obviously I could write hexane, but hexane is for straight chain sigma bond, but here we have triple bond, so it's hexine. Where's the alkyne triple bond? Well, it's at carbon number 3. And then what are the functional groups we have? Well, we have 2 methyls, 1 at carbon 2 and 1 at carbon 5. So we have a 2, 5, and we have 2 methyls, so it's a dimethyl 3-hexine. And now for C, let's once again identify the longest straight chain. So let's just arbitrarily choose this point, 1, 2, 3, 4, 5, 6, 7, 8, 9. Or we can choose from up here, 1, 2, 3, 4, 5, 6, 7, 8. So obviously the initial one that I counted from is correct. So let's figure out how we can get the alkyne at the lowest carbon number. So let's start from the left again. 1, 2, 3, 4. This gives us 4 alkyne. We start at the right. 1, 2, 3, 4, 5. So we know that 4 is preferred over 5. So this is going to be, we have 9 carbon chain, so it's a nonane, but it's actually a nonine because of the alkyne. Where is that alkyne? It's at carbon 4. And then what do we have attached? Well, we have at carbon 3 an ethyl, at carbon 6 another ethyl, and at carbon 7 a methyl. So adding it by the order of the alphabet, E comes before M, ethyl, methyl. So we know we have a 1, 2, 3, so 3, 4, 5, 6, so 3, 6. We have how many ethyls? We have 2 ethyls, so it's a di-ethyl. Then we have a methyl at carbon 7, so 7 methyl 4 nonine. So this is the name of this molecule. And now for D, using the same logic, obviously we want the alkyne to be part of the parent chain and at lowest number, so we can start from 1 over here. So 1, 2, 3, 4, 5, 6. So that'll give us 6 carbons, but what if I include the top? 1, 2, 3, 4, 5. No, that's not correct. 6 carbon is longer than 5, so we know that our straight chain is a hexyne. And not only that, it's a 1 hexyne, because the alkyne exists at carbon number 1. And then at 1, 2, 3, carbon 3, we have 2 carbon, it's functional group. So that's an ethyl. So at carbon number 3, we have an ethyl. Now for E, obviously if I count from here, I would have a 2 alkyne versus here I would have a 3 alkyne. So I'm going to start from the right. 1, 2, so 2 alkyne, 3, 4, 5 alkyne, 6, 7, 8. So I have 8 carbons here. So that's octa. And then we have 2 alkynes, so it's all octa diine. And where are those alkynes? Well, a carbon 2 and a carbon 5. So a 2, 5 octa diine. So F and G were actually given the structure, so we're doing some work for us. And so let's identify the parent chain. So we know that the parent chain has to have alkyne at the lowest number, so we'll start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So right away we know that this is going to be a deca. Deca. But now, deca. But now we know that the suffix is going to be "-ine", and actually we have, so interestingly, we have an alkene and an alkyne. So it's actually going to be what comes first. So the alkene will come first, is the lowest number. So we have a 2 decene. Remember, ene is for alkene, ane is for an alkane, and ine is for an alkyne. 2 decene. But then we also have a 6 ine. Why is that? Because at carbon 6 we have our triple bond. And the reason we don't count from here is because then all of these double and triple bonds would have a larger number of values, but we need to minimize the number of values. So now we have our 2 decene, 6 ine, and now 1, 2, 3, 4. Let's identify the functional groups. So carbon 4 we have an ethyl, and carbon 5 we have an ethyl. So we actually have a 4, 5. How many ethyls? 2. So that's di. Ethyl, 2, decene, 6 ine. For the last problem here, so when you have something that looks like this, you want your parent chain to include the cyclic structure. So here we have a cyclohexane, so cyclohexane, but ane, remember that's suffix for straight chain carbon, but we have a double bond in it, so it's cyclohexene. And now we need to number it such that the double bond, is at the lowest number of carbon. So let's start counting from here. So we have a 1, 2, 3, 4, 5, 6. At carbon 6 we have 1 functional group, that's a methyl. And then at carbon 1 we have 2 carbons, so that's ethyl, but it's not just any sort of ethyl. It's ethyl with a triple bond. So we know that we're going to have a 1-ethynyl. So remember the yn is the suffix for an alkyne, and then ethyl, we have to add the yl at the end. And then we have methyl at carbon 6. So remember, you add these according to the alphabet, so E becomes first over M. So we have a 1-ethylene, 6-methyl cyclohexene.